And so I'll also post their presentation, and that'll be a good introduction to some of the stuff we're going to do on Tuesday. So if you could watch that presentation before Tuesday, and then the introductory video, then we'll be good. And I'll send out information about all that. So any questions about anything before we start? And again, if you have questions about the group, we can certainly, when I meet with you, we can talk about it. Okie doke. So I'll open up the rooms, and then once everybody gets apparated, I'll start kind of, visit you all briefly. And you can tell me I'm in the way if I poke my head, and you can say, get out of here.
How's it going? Oh, we got the dock camera. Nice.
Yeah, you do. So I'm going to interrupt, and then I'll leave. But so Jackson told me that he's got some issues at home, and I assume he's communicated with you all.
No. He did not tell us. No.
He's not going to be fine though. So I'm going to put you in the spot. And has he been able to contribute? If not, I'm just going to have to do something else. So.
Not much, really. I mean, that first day we kind of figured out the thing together. But
okay,
I don't know. Well, I would say yes, a little bit yes.
Some yes, and some, but not recently. He's got some stuff going home, which is serious. He had to go home with his mom, and I think something with his grandfather too.
That makes sense then.
So he emailed me today, and so anyway, I just wanted to let you all know, and then. I hope that doesn't put you at a disadvantage for today.
No, we'll be fine.
Okay. And then, we'll have like a debrief of like where you just fill out a brief thing about how people can contribute. And since he's reached out to me, it's not a surprise, even though it might be for you all, but I'll work something out with him. Okay. So any questions about what you're doing? Or any questions for me about what you're doing? Let me put it that way.
Not really. We're just we got a PowerPoint we're gonna run through.
Okay.
And that would be it.
And so will 10 minutes be enough time?
Oh yeah. Yeah.
For you to do that? Okay, good. Okay, that sounds good. Okay. I'll leave you to your work then. Okay. Yeah.
Thank you.
Bye. I'm just going to break in briefly. I'm sorry about to interrupt you, but I think you know that CG is, you've probably figured this out. I think I told you she's just her connections issues are really bad, and so we're going to do a separate project. And I assume you haven't been in touch with her about this.
No.
Yeah. Figured. Okay, good. Just wanted to let you know. And do you have any questions for me before I leave?
I think I asked this question before last time. The problem like AX plus BX equals C.
Right.
So do I have to change my drawing, like just cut off the negative button here? I mean, the sign here.
No, it's okay. I mean, it depends. I will work with what you do. Just you're looking at C as a negative number, right? So it would be minus C over A.
I do have one example, but it's a rush draft. I didn't really clean it up.
Let's go back. Let's go back to your picture.
Okay.
So if you have an area here, that has to be positive.
Yep, that makes sense because there's no negative number for length, right?
Right. So minus C over A would be a positive number. You're just using C as negative. I tend to use it as positive and put it on the right side, but it's equivalent. So no worries.
I see. All right.
Okay. Anybody else have a question?
No.
Okay, good. And I'll have like a post. I'll post like a post presentation sort of debrief where you can talk about each other's contributions and stuff like that, and about the process itself. Okay, so I'll leave you be. Okay, I'll give you about 10 minutes or so. That'll give you enough time.
Yep.
Okay. Sorry to interrupt. Yep. Bye bye. I thought you'd be going over your presentation, so I see everybody's muted.
We've already done that.
You've already done
Yeah.
it? Okay, that's good. So you don't need any extra time then. I'm giving everybody about 10 minutes.
We know what we need to do.
Okay, good.
We're ready.
You'll just see me back in the main room. I'll give you a 30-second warning.
Sounds good, thank you.
Yep.
Okay. Bye-bye. I assume it's under control?
Yes.
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 I'm giving.
You're in our way, Dr. Alexander. Get out of here.
You'll get out of here. See you in about 10 minutes back in the main room.
All right, thanks.
You all ready?
Yeah.
Good. I'll bring everybody back in a minute. Okay. Everybody ready?
Never mind.
Kind of.
Kinda, yeah.
Yeah, almost.
How much, like we need to get them done, so a couple more minutes?
Yeah.
Okay. So I'll give you like a minute or like about 2 minutes. So it's what? 5:15? Yep, so 5:17.
Okay.
Okay.
Yeah.
Okay, yep, bye-bye.
Bye-bye.
I think everybody's back. Yep, okay. Okie doke, so group one will start. Is there anything I need to do to set you up?
Just make sure, make it so we can share screens.
Okay, that should, you should be able to do that now. Let me see if there's
Yep.
any, okay. Right, you should be good, okay. So whenever you're ready, I'll let you go.
Sounds good. Bryce, are we ready to go? Are we ready to go?
Yeah, I'm good. Can you guys see the screen?
Yeah. Did you want to show the screenshot?
Oh,
Like,
right. That's what I was supposed to put up.
Yeah.
There it is.
Perfect. All right. Hi, everyone. We're group one. It's Nick, me, Bryce, and Daniel. And today we're going to be showing you guys a Babylonian word problem. And I think this is a common theme throughout all of our presentation, but the solution is kind of emulating, or rather concerns, a quadratic equation. So that word problem is I have added the area of my square and 2/3 of the side of my square, and it is 35/60. What is the side of my square? I'm going to pass it off to Daniel now. Hopefully you see that they leverage false positioning in their equation, kind of like the word problem we went over previously. So yeah, I'm going to let Daniel take you through it with base 60 and then base 10.
All right, so the Babylonians had a strange method of doing this, as Paul was saying, false positioning. So this is what a textbook of theirs would have said. The solution to this would be, so 2/3 of 1 equals 0 semicolon 40, which is the rotation in base 60. This is how they would write stuff like this. Whatever's after the semicolon is in kind of a decimal place, and you can think of this as 40/60, which would just be 2/3. After that, you multiply it by itself. So you divide it by 2. You get 0 semicolon 20. Then you square it. You get 0 semicolon 6 comma 40. After that, you add it to 0.0 semicolon 35. And we get the result of 0 semicolon 41 comma 40. We take the square root of that. We get 0 semicolon 50. We subtract 0 semicolon 20. And our answer is 0 semicolon 30, which would be the side of the square. And if we kind of run through this in our base 10 system, the same steps, we see that we would get to the same answer. So 2/3 times 1 equals 2/3. Just divided by 2, we get 1/3. You square that, you get 1/9. You add it to 7/12, you get 25/36. You take the square root, 5/6. 5/6 minus 1/3 equals 1/2, which if you convert to base 60, you would get 0 semicolon 35. So this is how the textbook would have kind of told you to do it if you were to be a Babylonian at that time. And now I'm gonna hand it over to Bryce to show you guys how this actually is the correct answer in our system.
We're gonna solve it like a regular quadratic equation that we would use. Now we're gonna build the base equation that they give us, which is just, we have x squared.
Well, Bryce, I'm having a hard time hearing.
Can you hear me better now?
Is it your Bluetooth mic again?
Oh gosh, I should check that. That actually might be the issue.
It's getting better, but you were strong before.
That's weird that it, my Zoom likes to just
it's
make my mic not work. Better?
Yeah, it's working better. I can hear you. I think probably others can too, if I can.
Okay. So we start with the x squared, which is the area of the square, and then we add the 2/3 x, and then we have that is all equal to 35/60, or 7/12. Then from there, we move the numbers around so that we get it in a form more like what we normally use our quadratic equations in. And then from this, we can get our A, B, and C. Which then we can start to put into the quadratic equation where x equals negative b plus or minus square root b squared, should be 4/9, minus, but since a c is a negative, it's going to be a plus total for a c, which ends up as 28/12, and then all over 2a, which will just be 2. And then we work through it as we go. This ends up as 25/9. Divide by 2 again. This gives us plus minus 5/3 over 2. And then finally, we get x is equal to 1/2 or x is equal to -7/6. But we only care about this one and not this one for Babylonian mathematics. And I'll pass that on and they'll be able to explain why we only care about one of the answers and not both.
Okay, so the reason there's only one solution in this quadratic is because the concept of negative numbers is a fairly new concept to mathematics. So the Babylonians did not think in terms of negative numbers. Also, it makes sense because lengths and distances not thought of as negative numbers just doesn't make sense to people. And in the case, and the problem also seems to be a rather simple word problem. And this might suggest that this problem was being taught in some kind of school lesson in the Babylonian times. And do we have anything else to say?
No, I think that's it.
Yeah.
All right, that's the end.
Okay. Well, good. I enjoyed that. And you covered a lot of ground with that. Rather than me comment on that, I want to make sure that we get everything done, and then I can go back and comment. Are there questions from other people? Okay, that sounds good. So we'll go on to group 2. The only point I think that I want to ask you to think about is this: how generalizable is the solution that they found? Like, could you solve other quadratics, and if so, what ones? I'll just let you think about that. Okay, so I'll let the second group get ready. And is there anything you all need from me?
No, I don't think so.
Okay, good.
Okay. So group 2 is introducing an alternative quadratic method. And Colin, if you want to go to the next slide, I can introduce our problem. So our problem asks us to find the length and the width of a rectangle where the sum of the length and the width equals 6.5, which, like previously mentioned, we're working with a base 60. So anything after the semicolon is over 60. And then the area of the rectangle is 7.5. So we were asked to find the length and the width. And our presentation will go through how the solution from the text, and then how the Babylonians solved it. And then we'll go through how the new way of the quadratic formula, how that's solved.
So here's the solution from the text. So again, this is in base 60, and we have this converted on the next slide. But so their solution was to have the length and the width, which have been added together, and you will get 3 1/4, and then you square 3 1/4, and you will get 10, 33, 45, and then from that you subtract 7.5 from 10, 30, 45, and you'll get 3, 3, 45, and then you take the square root of that, and you'll get 1 3/4, and then to that you add 6.5, and then subtract it from the same quantity, that is 6, 30, or 6.5, and you'll get the length and the width. And so they get 5 gar, which is the unit of length that they used. So they say 5 gar is the length, and 1.5 gar is the width, is what they end up with. And so, like I said, the gar is a unit of length, and it equals about 6.5 yards. And the Babylonians also used the symbol. They had a special symbol for 1/2. So the expression 1.5 is historically correct. But so I guess the question is, why does it work?
So going a little more in depth on the Babylonian solution. So their first step is they took the length plus the width and divided it in two, and they got 3.5, which it, or yeah, no, 3.25, sorry, which we get the same product converted into like our version of numbers. And then they squared the half sum, and they got 10, 33, 45, which is the same for our numbers too. So then from that, they subtracted the area and got 3, 3, 45. They took then the square root and got 145. And then they knew that the length is the half sum plus the square root, so they got 5. And the width is the half sum minus the square root, so they got 1.5, which is consistent with the our numbers too.
Okay, and then so finally, we're gonna watch the part of this video that we were given to kind of show you the new way to do a quadratic, so you can kind of understand that, and then we'll run through it using the same numbers and see how it works. Hopefully the video loads. If not, we can just skip it and I'll explain it.
I don't think the audio is coming through, Colin.
We have the subtitles, so that's working.
Okay. Okay.
Yeah.
We'll run with it.
Or for me, it's working.
Okay. I don't know how much of that you guys ended up getting, but I can kind of explain it. So the whole point is that it gets rid of the idea of having to guess and check what the factors are by setting up an equation to do that. So we'll do it for our example. So first you got to set up and find the quadratic, which you do by taking the two equations we're given, length plus width equaling 6.5, and then length times width equals 7.5. You solve the second one for L, plug that into the first equation, and then you get the quadratic by multiplying all of it times W. So you get width squared minus 6.5 width plus 7.5 equal to 0. And then so you use this new method of solving a quadratic to find the roots for that. So you set up two numbers equal to the sum, which is our B value of 6.5. So you get 6.5 divided by 2 plus or minus U. And then you multiply those two together, 6.5 divided by 2 plus U times 6.5 divided by 2 minus U to get their product. So 6.5 squared divided by 4 minus U squared. And you set that equal to the C value of the quadratic, which in this case is 7.5. Then you solve for U, which you end up finding the square root, and that is equivalent to U being 1.75. You sub that back into the first equation of 6.5 divided by 2 plus or minus 1.75, and that gives you the two roots, or the length and the width, as 1.5 and 5. And so that's basically it. Does anybody have any questions? I think that's the end of our presentation.
Okay, good. No, I may come back with the question, but you showed how it fits with this, and I think that's really interesting. I'll have something more to say about that later. But it was good. Okay. So any questions? Okay, good. Let's go on to the third one.
All right. I'll share my screen then.
All right, so in our presentation, we're going to show completing the square. And this is something that most everyone would have learned in high school to some extent. And we're going to kind of show how it fits in with the quadratic formula. So basically what the Babylonians did was how we had a regular polynomial, which would be ax squared plus bx plus c equals 0. What they did was they literally made a square, and then they had another rectangle that they would add to it, and it would be a square because x squared. And they would have another rectangle they would add to it, and to do that they would take two sides, they would split the rectangle down the middle and stick it onto the ends of, or I guess 2 sides of the square, and then that would equal the area, or it should equal the area that we need basically, but we're missing a certain section of that. And so we need to try and find the area of that extra square. And Hannah, I'll throw it to you.
Okay, so in finding that the additional square that we're missing, we've got the smaller sides of the rectangle, the b over 2a, and effectively we can find the area of that smaller square by using those 2 smaller sides and just finding the area of that, which is just squaring the 2 of those. And then because we're adding it on, we're going to add it on to the original equation as that b squared over 4a squared, but we're adding it to both sides. So you're adding in an additional like smaller rectangle to the other square that you're solving for. And in doing that, you can then start to transition into where you're solving for the actual quadratic formula. And as you can see, because it's highlighted in a brown font where it starts to transition, and effectively, once you've gotten, you've done the algebra and you've gotten one side over into that b squared minus 4ac over 4a squared, that you found the total area of that new square. But further on, you can take the left side of the equation and start like unfactoring it, taking the square root to the right side and doing a bit more algebra, and you'll find the original quadratic formula.
All right, so I think I'm gonna take over now. That's basically the quadratic formula that we found using completing the square. It's just simplifying the method. But at the same time, I was curious about the completing a square as well, because back in high school, we do that a lot, right? I'm sure everyone here as well. But back in high school, I did it in a graphical way, where I tried to find a coordinate instead of what the Babylonian do, like using 2 square like area and stuff. So we do this, and I never really get the idea of why we do this. It's just to find the minimum point or the maximum point. At the same time, I try to put this equation into the quadratic formula, but it doesn't work because the square root end up to be a negative number. And I'm just confused about it, Dr. Alexander. Can you explain that to me as well?
Tell me, I was just making a note on something. Tell me again.
All right, so do you see the equation that I have here, the y equal 3x? So I try to plug this value into the quadratic formula.
Right.
But it doesn't work. But for some reason, completing the square makes me find the x instead of using the quadratic formula.
Okay. Well, let me see, because if you plug in, so you when you use a quadratic equation, what are you plugging? I'm a little confused over what you're plugging in and where.
So
Are you plugging in the original equation, or are you plugging in this version that's squared?
I'm plugging into this one, the final one.
But what are you plugging in? Are you plugging in the y equals 3x squared minus 9x plus 7, or are you plugging in something different?
So I plug in the b as -9,
right?
A as 3, and c as 7.
Uh-huh.
So in the end, I'll find a value that is square root of negative number,
Right.
which you couldn't do that.
I think that's going to mean that that equation you picked isn't solvable.
But it was solvable by doing computing the square, though.
No, that's a different thing. Look where your vertex is. It's at, I see what your question is. It's at 1/4, right?
Uh-huh.
That's the low point on the graph. So the low point on the graph is above the x-axis. That means there's no x value that makes that 0.
Okay.
Okay, and I will I'll show you what I mean when I talk about, because I was going to show how you can use this to solve the quadratic, and then when I do that I'll explain what I meant here. Here your vertex is above the x-axis, so the graph never crosses the x-axis, so there's no real solutions. So when you plug in the b squared minus 4ac, you're going to get 81 minus 4
84.
times 21. Yeah. So you're going to get a negative number inside the square root.
Yep.
Right. And it's a small negative number because you're just a little bit above the x-axis.
I see.
Yeah. So if you had a smaller 7, then it would work.
Yep. That's pretty much it
Yeah.
for computing the square.
Yeah. Okay, good. So it was good to compare it to the yeah. Okay, good. I like what you did. Okay, so I guess we'll go to any questions about it. Again, I'm going to save my questions for the end. And I do like the way that if you had a question about something that you asked it, to me to clarify something, that's fine. But any questions from the class? Okay, so I'll let group 4 go.
Okay, I'll share my screen. Okay, so our subject was the Babylonian completing the square, literally, because they used geometry. So the problem is you start out with a rectangle with length L and width W, and you know that length times width is going to be C, and length plus width is going to be B. So what you can do is you can add on the width to the original length of the rectangle and cut that in half. So on this side you'll have length plus width divided by 2, and that leaves you with this little portion of the original rectangle. And if you compute what the length of that would be, it's the original length of the rectangle minus this portion, length plus W over 2, and that will give you, and that will give you length minus width divided by 2. And this portion of the rectangle is important to helping you complete the square, which we will talk about next.
Okay, so what we take is that red rectangle from before and we kind of rotate it down to the bottom where the width from before is now the length, and we can see that calculated value is now the width. Now we literally need to complete the square and find the area of that green square right there. So in order to do that, we can calculate the length of the green box by taking that whole length at the top and then subtracting the width of the box to the left of the green box there and simplifying it to get length minus width divided by 2. Then we can also see that the width of the box is the same thing, which makes this green box a square.
Yeah, so as you can just see, we calculated that this mysterious green box that we knew about is actually a square with the area length minus width divided by 2 squared. And so we have to account for that by adding in the green box. we have to add to C the same amount of area. So now our total area inside this big square is C plus length minus width over 2 squared. And so if you take the side lengths of each sides of the big square here, we know that length plus width over 2 squared, so the entire square, is equal to what we just calculated, C plus length minus width over 2 squared. And then we can simplify a little bit by substituting B for L plus W, because that was given. And then finally, we take the square root of both sides to get our final answer. B halves equals square root of C plus length minus width over 2 squared. Any questions?
Okay. Good. So what I'm going to do, first of all, I'll give people a chance to ask questions. It always takes longer on Zoom. Okay. And you can ask them in the chat too. Okay. Okay. So I like these. I mean, it was fun to listen for a change, you know, and I thought you all did really nice jobs, and the presentations were visually appealing, and you got to the key in the core of each one. And what I want to try to do is sort of tie it all together. And a couple of questions. What the overall thing, as you all realize, is the Babylonian approach to the quadratic, and we have both in the length and width problem and in the square plus rectangle problem. You saw ways to. Oh, sorry, I didn't mean to. I thought my video was on. Sorry. You saw ways to solve particular equations, and they worked. And if you compare them to the regular quadratic equation, you get the same answer. And so that was one point of it. And then for the geometry, is each of those methods correspond to a visual way to solve the problem. And the speculation is, we don't know how the Babylonians figured stuff out. They didn't tell us. As somebody pointed out, you know, it's a really sound speculation to think that these were instructional, and that they were there to teach people how to do stuff. You know, in this case, solve the quadratic. And so, but we don't know how they came across these solutions. And so some people have come up with these speculations that they could have done this geometrically in the way that the groups that talked about the quadratic equation did. So that's kind of the big picture. And notice there were two types of quadratics here. I'm going to go to the document camera. I'm going to pin just so I can hopefully not run off the page. I may ask people to put their screens back on at some point. We'll see how that goes. So the first one was a square plus a rectangle is equal to some other area. And there was a solution for it. And so one of the visuals was this. I think it was group 3 that did this one.
Yeah.
And this is equal to some area C, and I'm just going to, do something like that. It doesn't even matter if what shape it is. It's just some area. And this is a plus, sorry. So what they did, again, I'm just going over what they did, is you cut this in half, and then you can add part 1 here and part 2 here. And so here you have x, and here you have b over 2, and here you have b over 2. And that's still equal to c. And then if you just look, it's clear that if you complete it, as people notice, that's equal to b over 2 squared. But you have to add that to both sides now, because it's that part is what's equal to c, so we have to do that. So notice what I have. I have x plus b over 2 squared. Sorry, x plus b over 2 quantity squared equals c plus b over 2 squared. Now notice, if I want to solve for x, what I can do, I can take square roots of each side. And since, these have physical things, so we're looking at sides of squares. Okay. And then what do I do to that b plus 2 if I want to solve for x? Well, subtract it from both sides. And if group 1, sorry, let me write that more neatly. And if group 1 looks at their solution, it's exactly this. That's exactly how the solution that you have, if you wrote it as a recipe, they're saying that x is equal to that c term plus that thing squared, cut in half, minus b over 2, as you pointed out. It's exactly the quadratic equation. And so this is one way they could have figured that out. And you can look at that problem and map it to this problem, and you see that they kind of followed the same steps. So it's reasonable speculation that that's what they did. Okay. And so that's one of the ties in right there. I wanted to point out. So to the Babylonians, that's what that quadratic was, with all the terms positive. And then to us, it's this. You know, that's how we would think of it, and we plug that into the quadratic equation. You'd subtract c from, you know, you'd consider that a positive. And notice that since c is negative, b squared plus 4ac is always going to be positive, so you never get a negative square root there. So because they set it up this way with this term positive and that term negative, you're always going to have a solution, and it's always going to work. And the difference in the quadratic is that we would put a plus and minus here, and then you would get one root that is entirely negative. Notice that this always has to be positive because of that c term. That's going to make c plus b squared over 2 square root a little bit bigger than b over 2, or a lot bigger, depending on the size of c and b. So this is always going to work, that particular form of the quadratic. And so my question is, this is for everybody, but especially people in group 1, because you thought about it more, could you generalize your solution, your steps, to any quadratic that looked like this? Like if the numbers were different. Like you mentioned it was false position. I was going to ask you about that. Could the solution that the scribe gave solve any equation that's of this form? If they had different numbers?
I think it could, since it was meant to be for kind of kids to just slap in the numbers and it should work out.
And I would argue that that's how a lot of us learn. Like you see a quadratic equation, and then what you do is you like, you know, you do a bunch of exercises and examples, then you finally get it. It's not this big abstract, insight. It's from doing equations, plugging in the numbers, and then, oh, I finally get this. And so that's kind of how I view what they were doing. They were giving you a step-by-step recipe, and you just had to figure out what numbers to use if it was a different kind of problem. And I noticed a couple people used false position. I was going to ask you why you chose that term, because I hadn't thought of this as false position until you say it, and now I think I do. So that's kind of an interesting, it's something I hadn't thought of before.
I thought you were looking for us to make that connection.
But let me ask this again. In what sense is it false position? Because I think you're actually onto something.
I think, and maybe I'm using false position incorrectly, but they're following more of an algorithm than we are in a sense, whereas we would plug stuff in, they're kind of using numbers to get to an answer.
Yeah. Yeah, and I think that's exactly it. That's the sense I think of it, and I never saw it as similar until you said that. And I think you're exactly right, especially because they used the side of 1, right? That was their example.
Right.
And so you could just, instead of 1/2, you could scale it up. You know, it's a little bit harder to scale up because it's a square root. It's not going to be a nice scale. But I said, oh yeah, that does make sense. Now I see why you said that, and that's actually, I think, an interesting point. So that's what I was looking for. That this is, I'm going to call this quadratic number 1, because that's one type of quadratic. that the Babylonians looked at. And if it was this form, a square plus a rectangle equals some other area, this is what you did to solve it. Okay, and by this I mean that the algorithm that they gave, and our speculation is that they might have used this picture. But I think it's kind of cool, you know, okay. Does that make sense? So questions or comments on that? Okay. So I'm going to look at the other problem, the length width problem, and those were related. And you did, you know, I think you did really good jobs of explaining them. Sorry, let me do this differently. Let's look at that quadratic, because those were the two solutions, right? One was the length and one was the width. So let me do it correctly. By the way, your visuals put mine to shame, so good job on that. So if I multiply this out, I get x squared minus lx minus wx plus L times W is equal to x squared minus L plus W x plus LW. And if, again, this is equal to 0 because that's how quadratics work. And now I'm moving the x term to the right side, so everything's positive, and I can look at this as x squared plus c is equal to bx. And where you're geometrically, you're linking b is equal to length plus width, and c is equal to length times width. So that's a different quadratic, and people gave a visual solution to how to solve this. And that visual solution would be hand in hand with the recipe that you saw. So the people that solved the length and width problem and the people that did it visually, those two things match hand in hand. You get the same solution. And I was going to look at something in the solution, but I wanted to follow this idea too. So I'm going to graph this. And I don't really care. I'm putting the vertex below the x-axis because we want the width to be the shorter solution and L to be the longest. And what do you know about the vertex? I'm just going to call it HK for lack of imagination. But what do you know about that vertex? How does it relate to the two roots? And think of the symmetry of a parabola.
It's at the center of them?
Yeah. So notice if this is M, and then this is U, and this is U, if we think of physical distances, then W is equal to M minus U, and length is equal to M plus U. And notice that both people who worked with this problem, that's kind of, remember you cut the length plus width in half? That's why. And so when we look at this, if we look at an equation, and I need one that's going to be solvable, so I'm going to cheat. And I'm going to move to a different page in a second. But that's my equation. So let's do that. X squared minus 8x plus 15. And we want to solve that. So remember that that's equal to L plus W. We see that right here. And this is equal to L times W. Sorry, that's equal to L times W. So we know that L is equal to the midpoint minus U. And then W is equal to the midpoint plus U. What's the midpoint? Think back to this picture. What is M equal to in this case?
The minimum?
Well, it's the minimum, right? But isn't the x coordinate? So the x, so that x coordinate h, how does that relate to 3 and 5? It's halfway in between.
So it'd be its midpoint.
It's the midpoint. It's L plus W over 2. So we know that M is equal to L plus W over 2. And we're thinking of L plus W as 8. We're really thinking of this equation. We want to think Babylonian. So we know that N is 4 in this equation. So we get 4 minus U, 4 plus U. Remember, length times width. And we get 16 minus U squared. And what does that have to equal?
Four minus U squared.
That's going to have to equal 8. Now my numbers aren't working out, so I don't like something I did here. I think I screwed up on something. Why is that? I put 8 there. What should that equal? Sorry, 15 minus U squared. What does it equal? I'm just stupid. Remember, this is length, this is width. And what's length times width in terms of this problem? Let's go back to look at this. If we solve that problem and put it out, B, we think of this as minus B, that's the B is going to be L plus W. And that's the C term, L times W. So what's the L times W over here? If we look at that equation, what's it equal to? $15. So that tells us that U squared is going to be equal to 1. So U is going to be plus and minus 1, or 1, because we're thinking geometrically. And so L is M plus U, W is M minus U. We know that M is 4, U is 1. So 5 and 3. So so to solve this equation, really all you need to do is you need to take 8, divide by 2, square it, subtract U squared from it, and set it equal to the C term, 15. And that's all you need to do to solve this, no quadratic. So notice if I look at this back, if I look at it in this form, so let me, before I go on and do that, does that make sense? And again, it has to do with our quadratic has L as one root and width is the other. So it's of that form. You multiply it out and you do the algebra, and that's the form that it is. Now I'm calling this B here, so but it's actually a minus B, of course, if we were going to, if we were to use the equation, and that's going to be our C. So this method is really, I think it's really brilliant, and because it's really short. This is all you have to do to solve the equation. And so like again, to me this goes directly back. That's the same recipe as that length width problems that you all did. I think it was group 2 did the problem, right? And then group 4 did the picture. Okay, so and I want to do one more thing with that, and then I think we'll be close to the end. So again, just to recap. That's what that equation ends up equaling, and that should be a minus. Remember, you subtract the roots. Okay, and then we do W plus L squared over 2 squared minus U squared is equal to L times W. So notice that this is going to be minus B squared minus U squared is equal to C. And then our answer is b over 2 plus and minus u. Do you see what u is going to be equal to? That's exactly the quadratic. So that's exactly the solution they're doing. When you were working on that problem, group 2, this is what you were doing. And group 4, you were doing the geometry for this solution right here. And again, remember that if we were doing this ourselves in the modern way, I'm writing it this way. But really, it's going to be something like this, where b is less than 0. Because negative positive number, it's going to work like that. And if b is less than 0, remember this term is minus b, or minus b, which now is going to be positive number. And we square that so it doesn't matter. But that new method, it really is a shortcut way to get exactly what the quadratic equation is. And again, when we were talking Tuesday, or sorry, yeah, it was Tuesday. We were talking Tuesday about different ways to think of math. Finding it using that video is, to me, is a different way than doing a quadratic equation. I might posit using the language of that article and using, some other things. That's a non-European way to think about it. And it goes all the way back to the Babylonians. Okay, and I think that's really cool. So any questions about that? Those are the tie-ins I'm hoping you're going to make. And I'm going to, we'll post, I want everybody to send me their projects. We're going to post those because remember, everything here was correct. There's nothing I need to really work on and say that wasn't correct. Everything was fine. This is your material along with what I say about this subject. And so I'm going to ask a homework question that goes over some of these ideas on one of the homeworks. Okay. But it'll combine different things. And I'll probably ask you to combine presentations 1 and 3 and 2 and 4. That way everybody has one of their projects involved in answering that question. Okay. So questions about anything? I have one more thing to say when we're done here, and that'll be it. But I'm hoping you make the connection between the length width problem in the video and that the second complete the square. And I'm hoping to make the connection between the first quadratic and the first complete the square. So groups 1 and 3 have a natural connection and groups 2 and 4 do. Okay, so here's the last thing. And we're going to use constants always being positive. So our a is 1, so we don't even bother with it. B is equal to 1. I'm sorry, B is greater than 0. And C is greater than 0. This is what groups 1 and 3 worked on. That's the Babylonian solution to this quadratic. And then in essence, the second quadratic, the length width problem, is really this. Where C and B are both positive. And then number 2 and 4 have a solution to this problem. Now, is there another form that we're always going to assume x squared is positive? Is there another form of the quadratic that would make sense for a Babylonian where everything has to be positive? So you can't have negative numbers. So you couldn't have x squared plus bx plus c equals 0, because in that case, sum of b and c would have to be negative. So can you think of another possible form of the quadratic besides this one and this one? Where everything's positive. How about this? A square is equal to a rectangle plus an area. Square, rectangle equal area. Square, area equal rectangle. Square equal to rectangle plus area. And we didn't do this. So when you think of the Babylonian quadratic equation, it's not one formula, but it's 3 procedures depending upon the physical nature. So they didn't, you know, as much as I like their solutions, at the same time, they didn't see all these as the same, at least as far as we know. There could be something missing, and I'll talk about that in a second, that we don't understand. But it's less likely in the Babylonian case, but still quite possible. So again, each of these had a different approach because of the physicality of the problem and the fact that, you know, things have to be positive because a negative length is nonsensical. And they would have had, the scribe would have had a different, you know, a different set of word problems for each one of these. And so you would have to learn 3 methods. And of course, I'm sure people realize, oh, these are all basically the same. There's just plus and minuses are different. I'm sure some people realize that. Okay. So one thing I haven't written about or talked about, and that's in part because of what we did on Tuesday instead of having the introduction, is that the Babylonians had a completely different way of writing than the Egyptians. And I'll talk about that in the video, but it's, in essence, the Babylonians took clay, wrote on it with a stylus, so they, you know, would gouge into it, like you might do if you were a kid and doing stuff when you were playing with Play-Doh or something like that. And then they put it in the oven, baked it outside. You know, Babylonia is like a lot of deserts. It's very hot. And so these things hardened. You know, if you ever did that with Play-Doh, you know, it gets hard, or cookie dough or anything. And then once they're hardened, they're like rocks and they last forever. And so we have literally hundreds of thousands, maybe even millions of documents from the Babylonian civilization. And they're written on these stone tablets, and they're pretty small. They're like the size of a Kindle. And so we know a lot about what they did. That said, there's lots of stuff that's missing. And one tablet we're going to talk about is broken, so we don't know what was on the other side. But so we have a lot more information about them. But again, we don't know what we don't have. You know, how many were destroyed, and you know, just over time, we have no idea. But because of that, we know a lot more about. We have a lot more artifacts from the Babylonian civilization that we do from Egypt. I mean, Egypt, we have those big temples. I mean, you know, we have pyramids and the Sphinx and that kind of thing. So we have those kinds of artifacts, but not nearly orders of magnitude different with written artifacts. So there's a lot more that's known about Babylonian mathematics. Okay. But what we can tell from what we know is that these were sort of different approaches to similar problems rather than a unified approach to all problems of its kind. Again, that's a Math 101 idea. You have the most general thing possible so it can apply to every possible situation. That's one way of looking at it. This is a different way of looking at it. Each situation is different, so you have a slightly different version of how to approach it. Okay. So I thought things were really, really good. I'm going to send out, I'll have a survey. I've already posted it, but I need to tweak it, so don't do it. One, about feedback on your groups, and the second about feedback of this process. I'll make that one anonymous, and the feedback on your group has to be personalized, because it's going to, if it's about people, I think you have to put your name on it. And then I'm interested in finding out a few things, like I made a note of some of those earlier. So let me just find it. It'll just take a second. And again, I will repeat this. So like what worked? What about this did you like? You know, do you like doing this kind of thing? I think it's really useful. Also, especially in the kind of remote class we have, because it makes you more involved. So did you like it? What suggestions do you have? Did I provide you with enough direction? What could I have done to have made this a better process? And this process, this particular iteration, was just so we could do something that was easily manageable and focus on all the mechanics of working with each other and, you know, and making the presentations. It looks like you all did a fantastic job of that. So the next one might be more challenging. I'm thinking about what it's going to be, and you know, you'll have it in a week or so. I think next week we're just going to go on with. We might have it by Thursday, but again, it'll be the same process. I'll give it out one Thursday, and you'll have a week to work on it, and then you'll have one. You know, I'll probably give it out on a Tuesday. It'll be due not that Thursday, but the following. And then you'll have at least a Thursday in class to work on it in class and talk to one another, and then additional time. Okay. Anyway, I'll write all that up. But anyway, I thought this worked really well from my point of view, and I really enjoyed the presentations and I thought everybody did a really good job. So I'm impressed. Okay, so comments. I'll be around for a few minutes if people have questions or concerns or anything like that. And I will follow up in writing about what I want you to do next regarding the project.
Have a good day, Professor.
Thank you, you too. I appreciate that, thank you.
Right. See you, sir.
Okay, take care.
Bye, Professor. Thank you.
Oh, good, thank you. I like the way it worked. Colin, did you have a question? I just see you're still here. Okay, take care. If anybody's there. Yep. Bye-bye.